So here we are. The new video is on bonding. Now, bonding. I consider this the most important chapter in high school chemistry. Why? Because you have to know the 3 chapters that preceded this. So you have to know atomic structure, protons, neutrons, electrons, isotopes, and ions. And really, you really have to know electron configuration, shells or energy levels, subshells, SPDF, and how to fill orbitals. Also, you have to know electron dot. And one of the most important ones is periodic table. You have to know the trends, electronegativity, ionization energy, and size. You have to know all 3 of those chapters before you can even think about understanding bonding. Okay? So bonding is the #1 most important chapter in high school chemistry, like I said before. And in this video, we are just going to do ionic bonding. That's it. The next video will be polar and nonpolar and covalent bonds. So we're going to start with the basic. We're going to start with a sodium atom and a chlorine atom. But before we do that, you have to understand something. In order to form a bond, there has to be a collision between the 2 atoms, like that. So when 2 things, I don't care what they are, 2 cars, 2 people, 2 bicycles, I don't care what they are, when 2 things collide, energy is given off, right? If 2 bikes collide, 2 bicycles collide, the people are going to go flying off, maybe some spokes are going to be going off, maybe a tooth this way, fingernail. So when a bond is formed, energy is released. The harder the 2 things hit, the more energy released, the stronger the bond. Now, how are you going to break a bond? You put energy in to break the bond. If 2 bicycles collide, you have to try to pull them apart. You have to put energy in to break the bond. So, once again, when 2 things collide, energy is given off, all right? So there's the bond. The more energy given off, the stronger the bond. But that means if you want to break it, you got to put energy in to break the bond. That's the first thing. So in order to have a bond, you got to have a proper collision. The next thing is this. When 2 atoms collide, nothing happens to the nucleus of each atom or more than the 2 atoms, which means nothing happens to the protons, nothing happens to the neutrons. Nothing happens to the inside shells of electrons. So in other words, nothing happens to the kernel. Remember, the kernel is the nucleus plus all the inside shells. But something is definitely happening to the valence shell. In particular, the valence shell electrons. So 3 things can happen to the valence shell electrons in bonding. They can either be lost, they can be gained, or they can be shared. So in this video, we are mainly going to be talking about valence electrons that are lost by metals and gained by nonmetals. Okay? So, like I said, we're going to do the standard 2 elements, and we'll go over everything. So here are the standard 2 elements. We're going to go with sodium, and we're going to go with the chlorine atom. So we're going to talk about the sodium atom and the chlorine atom. Okay? All right, here we go. So we have this, Na11, and we have this, Cl17. So remember, the atomic number, if it's an atom, the atomic number tells you the proton number, but atoms mean they're neutral, So we have 11 protons, but we have 11 electrons. Here we have 17 protons, atom of chlorine, 17 electrons. All right, and here's what the dash looks like. The dash for chlorine, 2, 8, 7. So that adds up to 17. So it's got 3 energy levels. The dash for sodium, 2, 8, 1. So we have sodium, it's in group 1 because it's got 1 valence electron. Chlorine got 7 valence electrons in group 17. Now, we are going to do the Bohr model of the atom because it's easier to see. So here's what we have. That's going to be the nucleus, all right? This is going to be the first shell, second shell, and third shell. All right, now over here, this is going to be the nucleus. We've got the first shell, the second shell, and the third shell. Now, in the first shell, we've got 2 electrons, so we're going to go like this. 1 up, 1 down. Remember, because in an orbital they have opposite spin. Now, in the second shell, we have 8 electrons, which means we have 4 orbitals. So we have an s orbital and 3 p orbitals. Remember how they fill, 1 in each, before 2 in any. And then finally, we have 1 electron in the third shell. Right there, that's 1 up, and so that's what that looks like. Now, electron configuration-wise, here's what it looks like. 1s2, that's that one. 2s2, 2p6, 3s1. So that's that configuration. Here is the valence shell configuration. Now over here, same thing. But in the third shell, we have 7 valence electrons. So we've got S, we've got P, 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 we have P1, P2, P3, P4, P5. So for this one, it would be 1s2, 2s2, 2p6, 3s2, 3p5. And here is the valence shell there. So over here, we have 1 valence electron, which means this is 1 valence electron. So the electron dot for sodium would look like this. Na with 1 dot for the S1. Na with 1 dot. Over here, for Cl, we've got 7. So we've got 2 in the S. Then we go 1, 2, 3, 4, 5. So we have 7 total in the valence shell of chlorine. So we got that and we got that. Now, remember, sodium is bigger because it's a metal and it's in group 1, and it's bigger than chlorine. Now, what is going to happen? Well, we have to look at the electronegativities. The electronegativity of sodium is fairly low. It is at 0.9. So the electronegativity of sodium is 0.9. While the electronegativity of chlorine is 3.2. So what does that mean? That means that sodium doesn't really have ability to attract electrons. And since it only has 1 in the outside shell, it probably wants to lose that 1 and then we can go to a stable octet in the second shell. So sodium wants to lose that electron. Chlorine, on the other hand, 3.2 electronegativity, that's pretty strong. And since there's 7 in the outside shell, it probably wants to gain 1. So this is how metals and nonmetals react. Metals usually lose, nonmetals usually gain. But remember, they have to collide. And once they collide, what's going to happen is, chances are, this 1 electron right here will probably go and get stolen by the chlorine right there. Okay? So now what's going to happen is this. Sodium's going to lose that 1 electron. Chlorine's going to gain that 1 electron. So what will happen is this. Now watch. What's going to happen is once sodium loses that electron, it loses the entire third shell. So now the ion of sodium is much smaller than the atom. On the other hand, chlorine is going to gain an electron right here. And that's another negative. So if you put another negative in a bunch of negatives, they're going to spread out more. So what will happen will be this. Instead of being this big, the ring, the third shell, will expand. And it'll have S, P, 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 and everything is going to be filled. So that is what has to happen. So the atom of sodium is bigger than the ion because the ion means it lost a whole shell of electrons. The atom here for a nonmetal is smaller than its ion because the ion gained electrons. So now, that's what happens. And now what we're going to do is we're going to do an electron dot diagram of NaCl. Okay, remember, they got to collide, and once they collide, there is a total transfer. Sodium transfers its 1 electron to chlorine, chlorine gets it. So here's what it looks like. We have Na, and we have this. Na has 1 electron, valence electron right there. Then we have this, plus Cl, and Cl has that. And remember, this is 0.9 electronegativity, this is 3.2 electronegativity. So chlorine is much more electronegative than sodium, so that means chlorine is going to steal sodium's electron. So here's what it looks like. We have Na with a plus there because that electron is going to go right over here. So we have Na plus. Now, whichever element gained the electron, I always like to put the negative ion in brackets to show that there was a total transfer. So I'm going to have brackets, bracket, and then I'm going to have the Cl right there, and then I'm going to have this. One, two, three, 4, 5, 6, 7. Then I'm going to show that electron from sodium right there. 8. So now chlorine has a stable octet, which means 8 valence electrons around it, but since it gained an electron, it's negative. So that's what it looks like. This is the electron dot for sodium chloride. Now, don't forget the brackets suggest total transfer. And the +1 and the -1, the charges or the oxidation states have to equal 0. If they don't equal 0, it doesn't work. So this would be Na plus Cl minus, and then it's going to be like this. solid. Na plus, Cl minus, solid. Now, another way to look at this is this way. We can say this is a crystal of NaCl. The smaller ions, remember, are going to be the Na pluses. And then the bigger ions, the ones that gained electrons, can be the Cl minus. So that is a crystal of salt. Now, don't forget, there was a total transfer. So my question is, if there's a total transfer, what's holding the Na plus to the Cl minus? Well, it's called electrostatic attraction. It just means the positive metal is attracted to the negative nonmetal, and that's what keeps them together. Okay, so this is a crystal of NaCl. Now, what you have to know about an ionic compound. Here we go. I'm going to do Roman numeral 1. Ionic compound. So the good thing about ionic compounds is when a metal loses an electron to a nonmetal, okay? And another name for ionic compound is this. Another name for an ionic compound is a salt. So there are hundreds of salts, not just NaCl. When a metal combines with a nonmetal, it's considered a salt. And it looks like a salt, right? It looks like a salt. And you know what salt looks like. So for number 1, the most important thing to know about ionic compounds, so there is a total transfer of valence, either one electron or several electrons. Total transfer of valence electrons. That is number 1. Now, number 2. We just talked about, well, what holds the positive and negative ions together? So, the positive ion and the negative ion, they're held together by electrostatic attraction. That just means positive is attracted to negative. That's all it means. So, going back, like I said before, ionic compounds are when a metal, and remember from here over, these are all metals, when a metal is attracted to a nonmetal. So we have hundreds of different types of salts. And the metals always want to lose, and the nonmetals always want to gain. That's an ionic bond. This. Now, this is where periodic table and electron configurator, this is where everything comes in. So, when a metal, now what do you know about a metal? They have this. They have large size, which means their valence electrons are pretty far out there. And if their valence electrons are far out there, their ability to attract electrons or electronegativity isn't very good. So, large size, low electronegativity. And if their valence electron is way out there, it won't take much energy to rip out that electron, which is ionization energy. So, when a metal, large size, low electronegativity, and low so, when a metal, which is big, lousy lousy ionization energy, so watch. So when a metal, like I said, big size, valence electrons way out there, can't really attract, so that's low electro, don't need very much energy to pop out the electron. So large size, low electro, and low ionization energy loses a valence electron or electrons to a nonmetal. Nonmetals are exactly opposite. So a nonmetal, instead of large size like a metal, it's small. And if it's small, that means the valence shell and the valence electrons are close to the nucleus, which means it's capable of attracting electrons. So, small size, and I'm going to shorten up for electronegativity, so small size, high electronegativity, but I'm just going to put high electro, and also high ionization energy. All right? So, when a metal actually loses valence electrons to a nonmetal, and here's the reason why. Okay? Now, there are three types of ionic bonds. The first one we just did. So, the first one is metal to nonmetal. We just did sodium and chlorine, but we're going to do a few more. And then we're going to go to the next one. So, for the first example, under metal to nonmetal, we're going to do this. We're going to do Ba plus Br. Now, Ba is in group 2. All right, that means it's got 2 valence electrons. We're going to show them with this. And Br is in group 17. It's got 7. S2, P1, P2, P3, P4, P5. So that's what those look like. But this is weird because barium wants to lose 2, but bromine only wants to gain 1. How is that going to work? Here's how it's going to work. We're going to put Ba And don't forget, if Ba wants to lose 2, it has to lose 2 electrons. Okay? So we got to put this. Plus 2. So Ba has to lose 2 electrons even though bromine only wants 1. And then, since there's going to be a total transfer, since it's a metal to nonmetal, we got to use brackets. Then we're going to put the bromine in there. We're going to put the bromine in there. Now, bromine only wants to gain 1. So if bromine only wants to gain 1, this is going to be a negative 1. Now, before we do anything, before we put the electron, valence electron dots in there, we have to make sure that these numbers equal 0. And the easiest way to make these numbers equal 0 is to crisscross and drop the sign. Super easy. So barium got to lose 2. Bromine only wants 1. So you crisscross. So that 1 goes here, and that 2 goes here. So what that means is I have 1 barium losing 2 electrons, but now I've got 2 bromines, each gaining 1, for a total of 2 gained. So now we can put in the dots. So bromine normally has 7 around it. 1, 2, 3, 4, 5, 6, 7. But remember, we're going to steal 1 of those from bromine, so it'll have a stable octet. Well, where did the other one go? Remember, there are 2 bromines. Each bromine gets 1 of those electrons. So now the correct formula for this ionic compound is just BaBr2. That's what it looks like. BaBr2. We'll do one more. All right, so we're going to start with aluminum, and then we're going to go with oxygen. Now, we're going to start aluminum. It's in group 13, so that has 3 electrons, which is an S2P1. So we have about 1, 2, 3 electrons in aluminum. Oxygen, on the other hand, is in group 16, got 6. 1, 2, 3, 4, 5, 6. So this is going to be really weird because aluminum wants to lose 3, but oxygen only wants to gain 2. How is that going to work? Well, let's see. Remember, they got to collide. Nothing happens to the nucleus. Nothing happens to the inside shells. It's only the valence electrons. So we're going to go aluminum, Al. It's going to lose those 3, plus 3. And then we're going to go brackets, which means total transfer. We're going to put oxygen in there. And we're going to put minus 2. So before we put the dots around, we lose 3, we gain 2. How is that possible? Remember, all you have to do is crisscross and drop the signs. So that 2 comes over here. 2 comes over here. And that 3 comes over here. Now, we're ready to put in the electrons. So remember, oxygen had 6 around it to start with. 1, 2, 3, 4, 5, 6. Let's erase this stuff. Now, aluminum wants to lose 3, but it gets 2. It only needs 2 more. There's 1 and there's 2. And people are going, but wait a minute. Oxygen only took 2, and aluminum wants to give away 3. Remember this. Here, you have 2 aluminums losing a total of 6 electrons, right? Here, you have 3 oxygens, and each oxygen wants to gain 2, so that'd be 3 times 2 is 6. So 2 aluminums want to lose 6 electrons, and 3 oxygens want to gain 6 electrons, so we are good. This equals 0, and this is one of the best examples. Crisscross, remember, you're always going to have a stable octet around the negative ion. All right, stable octet means you got to have 8 around the negative ion. Okay, so we'll do one more. K plus N. K is in group 1, which means it's an S1 configuration, and it's got 1 electron it wants to lose. N is in group 15, which means it's got 5. S2, P1, P2, P3. So this one is going to be kind of easy. Potassium wants to give away 1, but nitrogen wants 3. So watch. K is a plus 1, which means it gives away 1. Brackets, remember brackets means total transfer. We're going to put N in here, and then we're going to check out N's charge. N's charge is this, a minus 3. So plus 1 and a minus 3, it doesn't equal 0. Crisscross and drop the signs. This 3 comes over here, and that 1 is given right there. You don't have to put it down. Now we put in the electron dots. Well, N had 5. So N had 1, 2, 3, 4, 5. And potassium wants to give away 1. But there are 3 potassiums. Each potassium gives away 1, which means it gives away a total of 3. 1, 2, 3. And that's how it works, and there's your stable octet. So don't forget, before you do the electron dot diagram, if these numbers right here, if the oxidation states don't equal 0, you must crisscross them. Okay? So this is the first type of ionic bond. What if the metal has more than one oxidation state? Well, here's one that we have to figure out. Watch. If I give you this name, copper, Roman numeral 2, iodide. So, copper 2 iodide. Well, you know copper is this, Cu. What does that Roman numeral 2 mean? Well, watch. If I'm looking at copper right here, copper can either lose 1 electron or lose 2 electrons. So copper Roman numeral 2 means copper plus 2. Doesn't mean take the second charge down. Whatever the Roman numeral is, that's the positive oxidation state. So copper can be either copper Roman numeral 1 or copper Roman numeral 2. Okay, so copper Roman numeral 2 will be this, copper plus 2. Iodine is in group 17. I minus 1 is its charge. Do those two equal 0? No. So all I have to do is crisscross. So that 2 goes here, and the 1 we already know is there. So the formula for copper Roman numeral 2 iodide is CuI2. CuI2. Okay? We'll do one more. Lead, Roman numeral 4, chloride. Well, the Roman numeral means plus 4. So this is Pb plus 4, Pb plus 4, Cl minus 1. Those two do not equal 0, so crisscross. So that'd be PbCl4. Okay, that's the first type of ionic bond. And those are transition metals. The transition metals, if you have more than one charge for the metal, they write it as a Roman numeral. Okay, so maybe we should do one more. How about this one? Gold, Roman numeral 3 sulfide. Well, the Roman numeral 3 means it's a plus 3. So AU plus 3, S is a minus 2. They definitely do not equal 0. Crisscross, drop the signs, and we're good. So it will be AU2, S3. And that is an ionic compound using a transition metal. Okay?